Welcome to tonight's event in the year-long series on Stanford campus, Imagining the Universe, Cosmology in Art and Science. I'm Matthew Tooze, I'm the Associate Dean for the Advancement of the Arts at Stanford, and I'm delighted to see you all here tonight. Tonight we've heard from artists about the universe, we've heard from poets about the universe, we've heard from astronauts about the universe, and tonight we are hearing from one of our major physicists about the universe, and we're very excited about that. This series has been a collaboration between units from across the campus, and it started really with a conversation with Peter Michelson, the chair of the Department of Physics, and has brought in the Cantor Arts Center, the Department of Music and of Theater and Performance Studies, Stanford Arts Institute, and many other organizations on campus to bring to the fore different ways of representing and thinking about the universe, from artists to scientists to poets to philosophers. And so we really are very excited to bring to the close tonight the series of speakers. But there's still more coming up. If you are interested in a cosmological approach to symphonic music, I encourage you to go to the performances of Nolan Gasser's Stanford alum's composition, Cosmic Reflection, which is going to be in Bing Concert Hall on May 16th and 17th. And if you're interested in theatrical approaches to thinking about the universe, the Department of Theater and Performance Studies is putting on a staged reading of Bertolt Brecht's Life of Galileo, which will be May 15th through 17th in Lathrop Library. So those are on the horizon. Keep an eye out for those. Tonight's event, however, is a talk by Professor Andrei Linde. Professor Linde is a professor of physics at Stanford University and one of the authors of the inflationary theory and the theory of inflationary multiverse. He invented the theory of chaotic inflation, which is the most general form of inflationary cosmology. He also helped to develop the mechanism of vacuum stabilization in string theory, which allowed it to incorporate the theory of inflationary multiverse in the context of string theory. He's the author of the books Inflation in Quantum Cosmology and Particle Physics and Inflationary Cosmology. And his honors include the Dirac Medal, the Peter Gruber Prize, the Fundamental Physics Prize, and the Kavli Prize. And among many other accomplishments, he's also a skilled photographer. So he's the perfect person to speak to us tonight about art and science and the universe. His topic is universe or multiverse. Please join me in welcoming Professor Andrei Linde.
So today's subject is relatively new, at least officially relatively new, because for a long time we were talking about the universe as the only possibility of describing our world. Then we started talking about the multiverse, but there was a strong backslash on us. Archbishop of Vienna said that this is against all principles of morality. One famous professor from Princeton said that it is destructive and dangerous to our society. So be careful, there's something dangerous going on here. But we will start slowly, we will return back to Albert Einstein. This is something which he had written in his autobiographical notes. It was 49, not long before he died, and he kind of summarized his life and his beliefs, what he thought is correct, etc. And there is something interesting in these notes, something which, well, let's just read it. I would like to state a theory which at present cannot be based upon anything more than a faith in the simplicity, intelligibility of nature. There are no arbitrary constants. What I mean is what he meant. Mass of the electron is just a mass of the electron. Mass of the proton is a mass of the proton. Well, the force of attraction between electrons are given by their charge, and the charges do not change in time, and they're everywhere the same in the universe. So he have a hope that nature is so constituted that it's possible logically to lay down such strongly determined laws that within these laws only rationally completely determined constants occur, not constants, etc., etc. So the meaning is God did not have any choice. In fact, he even formulated it like that. I am not interested in this and in that and in that. I want to know whether God had any choice in creation of our world, literally from his writing. Okay? So that was the idea with which all of us physicists were living our life, thinking that our goal is to find this unique set of laws such that only these laws, this set of laws, are logically possible. Everything else must be wrong. For whatever reason, we may not understand it like children, we do not know the truth, but we are going to experimentally determine what these laws are. And when we determine the role of physics will be over, then it will be chemistry, engineering, everything. But we are going to find the fundamental law of our world, and this fundamental law must be beautiful and unique. Not only this idea was supposed to apply to the laws of physics, but also to the universe as a whole. Because when we look to the right of the universe, we look to the left of the universe on a very large scale, we see the same type of galaxies, planets, everything here and there, everything is the same. It is distributed with enormous accuracy, and this was called cosmological principle. So the universe must be uniform because of the cosmological principle, okay? And I used to make a joke that some people who do not have good ideas, they sometimes have principles. But then I learned that this principle also was invented by Albert Einstein. Actually, it was used, in fact, by Newton also, long time ago. Everybody wanted to have a definite system of rules and definite description which would apply to everything simultaneously. Then what we're doing makes sense because we're discovering the law, and once we discover it's for everyone to obey. Okay? So now our goal as cosmologists in the beginning was to explain why the universe is everywhere the same, because that's what we see. Well, it's not literally the same. Because in the solar system, you have lines, different lines in different places. In our galaxy is different from intergalactic, outer galactic space. There is no stuff there. Here's a lot of stuff. But if you take our universe in average here and there, at the distance much, much larger, well, the largest distance which is, our best telescopes can see, we will see that here and there, density of matter in the universe is the same with accuracy better than 1 in 100,000. So how is that to polish the universe? This was a mystery. We wanted to resolve this mystery, and as you will see when I will describe inflationary theory, we have right now a mechanism which explains why the universe that we see right now must be uniform. But then, when we continue developing this theory further and further, we were up to a surprise, and this is the surprise which is so dangerous for society apparently. So let's see. So first of all, I actually even wanted to show you this in writing, because it should be then later written on all these people autobiographies. This is what I said. Oh my God. Okay. So what was before the Big Bang? This is one of the questions which was bothering people for all the time. Like, our universe emerged from what? Okay. What was before the Big Bang? And when I was a student, I was learning physics and astronomy, and I was reading books on general theory of relativity, and it was written there that the solutions of Einstein equations cannot be continued to the negative time, that means before the Big Bang. Okay? And therefore it does not make any sense to ask the question what happened before that. So it doesn't make any sense to ask the question what everybody asks, so yeah. Okay, so this is one of the things. Why is our universe so uniform? So this word, universe, uniform, that's why it is universe, not only because it's the one, but because it's everywhere more or less the same. Why it is so uniform? This question was addressed long time ago, in the beginning of 70s, by famous British scientist Stephen Hawking. You know him, of course, okay? So he, together with his colleague Collins, have written a paper which contained in the end of it the following sentence. So they were trying to find out whether you can start with whatever garbage you want, and then eventually get our beautiful universe. Okay? So the conclusion of the paper was formulated in a very mathematical language. It was like that. On the set of all possible initial conditions, the set of those initial conditions which bring to us the universe of our type has measure 0. Okay? Yeah, it is very formal, but translation into normal English means no way. Okay? So no way you start with something and then you get the universe like the one which we're living in now. And then therefore in the concluding sentences he needed to find some way nevertheless. And he said, but if we take genetic initial conditions which would lead to a very terrible universe, then it would be unsuitable for human existence, and therefore in the universe where we can live, we do not ask stupid questions. Our universe. That was a very tricky answer, and this is a very smart answer. It is based on so-called anthropic principle. And anthropic principle is a very good, interesting construction, except for, well, why God would need to work that hard to make the whole universe so nice and cozy? Because if he wanted us to exist, it would be enough to have some nice conditions in the vicinity of the solar system. Why bother any further? So this was not quite convincing explanation. Also, why the universe is not exactly uniform? What do I mean by that? Well, galaxies are non-uniformities. And they're very important non-uniformities because we are living there. It's our cosmic home, galaxies in our solar system. So if you have a principle that our universe must be uniform, and then on the other hand you have galaxies which are a little bit non-uniform, it looks like it's not a full principle. You cannot call the man who takes small bribes a man of principle. So similarly, if your universe has a principle that it must be completely uniform, but it is okay for it to be a little bit non-uniform, this is not a good principle. We need to have explanation. Why it is isotropic? What does it mean, isotropic? Well, the universe, everybody kind of think about it like something spherically symmetric. You are in the center of it, or maybe there is no center, but it's in all directions is the same. In all directions of the same means isotropic. Roughly speaking, it is a sphere rather than a cucumber. Okay? So why our universe is not a cucumber? A different question. Our Earth is rotating about the sun. Our sun is rotating about the center of galaxy. The whole galaxy rotates. Okay? Our universe does not rotate. There is no axis, okay, about which the universe rotates. How do you know that there is no axis? Because there are some experimental data. Very, very careful. Right now, from the satellites, they're checking whether there is some a little bit of, well, preference in this direction and that direction. And there are some constraints and, well, suspicions at the level of maybe 10 to the minus 5, something totally miserably, and nobody knows for you whether there is or not. So the best hypothesis at the moment, the universe does not rotate. So why everything rotates, the universe doesn't rotate? Why all parts of the universe start expansion simultaneously? What do I mean by that? Well, just look at the part of the universe which we see right now. We see the part which is at the distance, the largest distance, is the age of the universe multiplied by speed of light, okay? I cannot see any further than that. Now I look to the left. I see also at the distance age of the universe multiplied by speed of light. Well, but the distance from this to that is twice the age of the universe multiplied by speed of light. So this part does not know anything about this part. How is that happening? That the density there and the density there is absolutely the same with enormously large accuracy. So that's a problem. Okay? Why the universe is flat? What do I mean by flat? Euclid told us that parallel lines do not intersect. They just continue being parallel. Now, if you have parallel lines at the equator of the Earth, they converge on the north and the south pole. And similarly, if our universe, which is open universe, has geometry similar to the hyperboloid, then the parallel lines, they diverge at infinity. And in our universe, they don't do this. Okay? So why, if Euclid was right? 2,000 years ago, the wise man said something without much experimental evidence, except for he would be able to draw some lines on the sand, whatever. But now we have evidence with all the best telescopes. We see parallel lines do not intersect. Why the universe is so large? And the answer to this, well, actually this question is related to another question. Why there are so many people in this auditorium? Many people came to the lecture. Or because there is Stanford University, many people around, and some people decided to come. But why there are so many people at Stanford area in general? Well, this is only some small part of the United States, and actually of the Earth, there are so many other people in different places. Why there are so many people here? Well, just think about it. This Earth is just one planet. There are many, many planets. Recently we have discovered about 1,000 of them. Now we're learning that every star has planets. Every star has planets in our galaxy, or almost every. In our galaxy, there are 100 billion stars. 100 billion planets, lots of people, some people live here, some people decided to come to the lecture. How come that our galaxy has so many stars? Well, actually there are 100 billion galaxies in our part of the universe. And why our part of the universe is so enormously huge? And then the father becomes angry and shut up. Our universe is big because this is the universe. Okay, so that's now. Okay, so here is the situation. What we know right now is that we still do not know what exactly happened before the Big Bang. However, some of the best explanations are coming from inflationary theory. And as for these questions, all of them have been answered by inflationary cosmology, which I'm going to tell you about. So all of these questions look almost metaphysical. And for a long time, nobody cared about these questions because it's like the universe is given to you, why should you question, okay? Now that when we know the answers, you cannot consider the questions stupid because we know the answers, so you cannot forget about them. So here is then some explanation of what is basic mechanism for inflation. Before I go to the details, I will tell you how inflationary mechanism was originally explained. It was an explanation which was not exactly in the form which I'm going to give you, but something close to that was given by Alan Guth, who was in the beginning was working here also at Stanford. And it was something like that. Again, I do not think that he would use these analogies, but maybe. Okay, so here is the box filled with matter, like a cubic meter of nothing, but there is 1,000 of candies inside. Now the universe expands, the size of the box becomes 10 times larger in this direction, 10 times larger in that direction, and 10 times larger in that direction. So the total volume becomes 1,000 times greater. How many candies you started with inside this matter? Well, you had 1,000 candies, you get 1,000 candies. But now they occupy 1,000 times greater volume. So if previously you had 1,000 candies per cubic meter, right now it's just 1 candy per cubic meter. Well, according to Einstein equations, the speed of expansion of the universe depends on the density of matter inside. So when the universe expands and density of matter decreases, the universe slows down. That is why the Big Bang is actually not so big. It started with a big explosion, but then it's very difficult for it to become really big to encompass everything that we see right now. Okay? So in order to produce our universe, you need to start with a universe which had originally mass approximately 10 to the degree 80, 10 to the degree 80 tons of matter. Okay? So before the Big Bang, it is nothing. And then after the Big Bang, you have this present, 10 to the 80 tons of matter from nowhere. That is all. God can give it to you, but who else? Whatever. So that was one of the interesting things. So now what inflation tells you? And I'm going to tell you something which will look totally wrong, but just bear with me for a while. Suppose you have a box filled with heavy, energetic nothing. Okay? So what does it mean? You have vacuum which has vacuum energy. And it would sound silly, but this is what some subjects for which people already got lots of prizes at this stage, because in '98 they made, people who study supernova, they made an experiment which I believe is one of the greatest experiments of 20th century. That is, they found that empty space has non-zero energy density. Okay, so it's really, it sounds, how is that? It's empty, it doesn't have anything. But in quantum mechanics, no, there is no theorem that empty space has zero vacuum energy. It's actually a problem. Why it does not have totally huge vacuum energy? And how to solve the problem, we will return to it in the end of the lecture. But here is the question. So why the energy density is so small, but non-zero energy density of nothing? Okay. So now, suppose that you have this cubic meter filled with nothing. Now this cubic meter expands 10 times, and 10 times, and 10 times. What is inside the box? Well, nothing. Okay, there is nothing. So there was nothing in the beginning, nothing in the end. But energy density remains the same. It's just a property of this space, property of nothing. So if you have energy density and then space expands, you have the same energy density, but the volume have grown 1,000 times. So the total energy, which is energy density multiplied by volume, have grown 1,000 times. Okay? Once again, so what is going on? You start with some limited amount of energy, and then the volume doubled and tripled and quadrupled and becomes 1,000,000 times more, and nothing changes yet. Okay? So then the total amount of energy inside the box becomes exponentially large if the universe continues self-replicating. And then this vacuum decays, and in every cubic meter you produce 1,000 candies. Then what you happen, you start with empty box, and then it expands, grows, and then decays, and you have enough candies to feed every child in the universe. Okay? So that is much more economical. You have nothing, and then you have everything. Okay, much more economical. You feel that it sounds like cheating, right? For many reasons. First reason is, how do you get everything from nothing? Because you know that there is this law of energy conservation, right? So if you have energy, energy is equal to mc squared, right? Okay. So then if your mass, you did not have practically mass, you have a small universe with this heavy vacuum, but very small volume. And then suddenly you have huge mass with this 10 to the 90, 80, whatever, tons of matter. How is that you get it from practically nothing? It's impossible. Well, the trick is, and the answer is very strange, but, well, trust me on that. So the answer is this. Total energy of the whole universe is exactly equal to zero. Okay? Exactly equal to zero. It is divided into positive energy of matter and negative energy of gravitational field. Okay? So zero remains zero. There is no law that total energy of matter by itself cannot grow. Okay? This again sounds like cheating, but you will see later. I will show you some equations. Okay? Not in order to solve them, but in order to show that we are not just talking this bad philosophy, but we are having something to say and to confirm. But the idea is actually the following. If you have one object of a mass m, another object of mass m. These have energy mc squared, these have energy mc squared, but they attract each other. And this energy of attraction is negative. I need to make some work to push this object to infinity. Okay? So if you have many objects in the universe and they all attract each other, then it's possible to show that the total energy of mutual attraction is equal to their combined mc squared, and therefore these two energies cancel. So in principle, it is possible to split zero into exponentially large energy of matter and exponentially large energy, negative energy of gravitational field. So that part we may be able to answer. But then another part is, what does it mean? If you have nothing, and we are talking about exponential expansion of nothing, what does it mean? Because if you have one point and another point, some object and another object, the person put there, then you understand what does it mean that the universe expands. But when you have exponentially expanding nothing, it does not mean anything. Okay? So this was actually the reason why the original version of inflationary theory by Alan Guth failed, did not really work. But then it was replaced by some other theories, and this is, oops, yes, thank you. Postpone, unless you want to learn more. Okay, so this was the model which I invented after we first I replaced Alan Guth model was something almost working, and this one is practically working. So this is the theory which describes something which is called scalar field. Now, scalar field is, yeah, that's another problem. We need to learn what scalar field is. But I have an analogy which should be helpful. Here you have 110 volt in the socket, right? Okay. So electricity works only because you have 110 and 0. If you have 110 and 110, there is no electricity. You need to have 110 and 0. If you have 110 all over the audience, it will not kill you, do nothing. Okay? You probably sometimes in your life were passing below these electric lines, high voltage lines, right? And you go under them and see the sound, okay, high voltage, okay? And then you see birds sit on this high voltage and nothing happened to them, right? Okay? Because for them, 10,000 volt does not mean anything. But you have probably never seen a bird which has one arm on one line and another on another line. Okay? Such birds immediately get fired. So they eventually evolutionarily disappear. So probably they don't do that. Okay? So the idea is this. If you have something like this voltage all over the room, then it's like vacuum state. You do not see it, you do not feel it, you just live in it. You can move through it, and in fact, this is something for which people already got their Nobel Prizes. We are right now surrounded by Higgs field, which gives every particle in our body some mass. That's why we are not flying with the speed equal to the speed of light. Okay? So since Nobel Prize is already given, it's probably true. Now, so suppose that we have, and this field which we are using is example of this kind of field. If it is constant, if it does not move, it's just another vacuum state. If it is here, there is no field. If it is here, then it is large, and it does want to go to the minimum where it will probably disappear. Okay? But the trick is, the universe does not let the field go fast. And this is something which we did not know 30 years ago. It came to us as a surprise, total surprise. What we learned, that if the field, the scalar field, originally is very large, not 110 volt, not 10,000 volt, but much larger than that, then the energy of the field makes the universe expand fast, and rapid expansion of the universe keep the field stick to the wall, so it does not fall down quickly. So I promised you some equations. I'm showing you these equations, not to solve them, but to point at them. So here is a little bit simplified Einstein equation, which show that the Hubble constant, which tells you what is the speed of expansion of the universe divided by its size, is proportional to energy of the scalar field. And here is the equation for the scalar field, which tells you that this is acceleration of the scalar field, this is the mass and the value. Okay, well, this is strange looking equation, but this is equation for harmonic oscillator. This is equation for pendulum. And you see that this is the same. So pendulum means acceleration of this is pendulum. Acceleration of it is proportional to how far it is from the minimum, wants to go there. But then there's an extra term which appears if you put the pendulum in some viscous liquid. So viscosity, resistance, this appears here. If you do not have this term, pendulum will be swinging. If this term is large, this is called overdamped oscillation. Overdamped means it goes down very, very, very slowly. Okay? So if this term is large, oscillator does not go down fast. If this term is large, scalar field phi almost does not change. Practically it remains the same. When this term is large, when the Hubble constant is large, Hubble constant is proportional to the energy of the scalar field. So when the energy is large, Hubble constant is large, friction term is large, and the field phi practically does not change. And then here is the basic idea. Large field, large Hubble, large friction, field moves very slowly. If field moves very slowly, then this part of the Einstein equation, remember, this part of the Einstein equation, okay, h is proportional to phi, h is this, so take the square root of it, you will get this equation. And this equation is by far the simplest differential equation of mathematical physics. And it has the simple solution that scale factor, the size of the universe, grows exponentially with time. Okay? But then, of course, it does not continue indefinitely. Scale field eventually goes down. When it goes down, speed of expansion of the universe slows, Hubble constant decreases, and when it decreases, friction term becomes small, scale field starts oscillating near the minimum of its potential energy. When it oscillates, it produces elementary particles, and the universe becomes hot, and the universe becomes hot after inflation. So the universe was not hot in the beginning. The universe became hot after inflation, after this field oscillated, produces particle, then we have what we call Big Bang. So not inflation after the Big Bang, but Big Bang after inflation. Now, here is then the basic picture illustrating what is going on. Let's start with the smallest size universe which you can imagine. You cannot go smaller than that because practically you cannot measure anything at smaller distance, because at the smaller distance your rulers become winding, unwinding, bending all the time. It's quantum fluctuations of metric of space unavoidable at this scale, and you cannot go any smaller than that. So let's take the smallest part of the universe and let us inflate. So in the simplest models of inflation, you start with that, and within this amount of time, you get the universe which has this size. And don't ask me whether this size is in kilometers or in miles. It really does not matter. It may be in microns, it really does not matter, because this number is so huge. So why it is important? Because you start from the tiny, tiny speck of space. That's where you started, okay? Conditions here and here could be easily the same everywhere there, but even if it is not the case, when the universe inflates, when the universe expands, just think about our Earth, and just imagine the radius of our Earth growing suddenly within 10 to the minus 35 seconds. Suddenly grows like that. So you have this Everest, the mountain, and then it would be stretched like that, and it will be a plateau. So the surface of the Earth would be absolutely ideally polished. Our Earth would be absolutely uniform and homogeneous. We will be looking at this step of space here because we cannot see all of this, because we can see only speed of light multiplied by the age of the universe, which is a minuscule fraction of the whole size. And that is why we see our universe uniform, because all the non-uniformities are thrown away, are stretched, we do not see them. That's why we see all parallel lines parallel, because nobody has seen these parallel lines crossing or meeting each other here because what we see is only in this area. That's why Euclid was right. So when you know that it is so simple to solve so many different complicated problems of cosmology, just like that, you say, my God, and maybe something's in it. Okay? But then you may say, but it's actually not so good, because we need to have these non-uniformities. So if we stretch everything away, then we do not have these galaxies. Once again, the same curse as before. Either you want uniformity or you want non-uniformity. How we can get both? Well, the idea, and that was tremendous. At the beginning, when we started developing the theory, there were some people along the corridor at Linde Physical Institute where I was working. It's Mukhanov and Chibisov, and they were saying some absolute nonsense. They were saying that we can create galaxies from quantum fluctuations. I say, come on. Okay. Quantum fluctuations, they are small. Okay, they are quantum. And galaxies, they are big. They are galaxies. How can you create quantum classical from quantum? 3 years ago, I was talking with Roger Penrose, and I explained to him that, look, Roger, that's what we're doing. We know how to create galaxies from quantum fluctuations. And there are some experiments showing that this is true. And he said, nope. It's impossible to create anything classical from anything quantum. So that was just amazing, because the person is supposed to be the great physicist who knows everything about everything. Anyway. So, it's a different story. It's a different so what happens is that galaxies are children of quantum fluctuations. You have these tiny quantum fluctuations, and the expanding universe stretches them exponentially. They become huge because of this friction term. When they are expanding, they stop oscillating. They just freeze. Okay, and then other quantum fluctuations. They spread also, stretch on the top of the previously frozen fluctuations, freeze on the top of the previously frozen, then another, then another, then another. And then inflation ends. And then after inflation ends, they all start oscillating, they become normal matter. And in some places where they interact, overlap constructively, these quantum fluctuations, you have galaxies. In the places where there was none of them, there is nothing. Okay, so that's how eventually galaxies form. Galaxies form like that. And how you know about that? Well, we send satellites to the sky. This baby cost about $1 billion. Okay, so it was flying and producing new and new data. There was actually many other experiments before that. But what they are doing, the result looks like that. Okay, so this is a set of spots on the sky, which is, okay, so here is explanation of the picture. When the Big Bang happened, photons, very hot photons, were moving towards us from all parts of the sky. But the universe was stretching, and these photons get tired. And when they're reaching us with very small energy corresponding to temperature. Temperature is a measure of energy. Okay, temperature 2.7 Kelvin. Absolutely minuscule temperature. Very difficult to create this one in the laboratory because we have so much, lots of temperature, lots of heat around. So that's why they send the satellite where things are cold. They're cooling them down so that you can distinguish on sky small fluctuations of temperature. So we knew that it's 2.7. We looked at the sky a long time ago and we see it's totally the same. Here and here and here 2.7 Kelvin. The universe is uniform. Okay? But then start looking and we've seen that in this side temperature is approximately 1,000th of a Kelvin higher than in this direction. And that was an interesting story. But then people realize that what happens is that Earth moves with respect to the photons. So when it moves toward the photons hit it to the face, it looks like this is a little bit more hot. Okay? Then we know how to subtract this from our data, and then no effect, and no effect, and no effect, and then at the level approximately 10 to the minus 5. Okay? Think about it, 10 to the minus 5 of what? Of Kelvin, okay? At this level, they looked at this and find these spots on the sky. So these people from Planck, they looked at that and they were absolutely ecstatic. They looked at that and said, one of these people made a mistake. They said in public that many of my friends would sell their children to see this image. Okay, that was a politically incorrect statement. but then they were, well, traveling everywhere in different countries, showing this image, and the question was, $1 billion for that? I just go to Home Depot and buy this spray and do it for you for $5. So it is important to understand what this image shows. This image shows imprints of these quantum fluctuations, which have been produced at billions of billions of billions of billions of a second after the Big Bang, stretched to the whole size of the observable part of the universe, frozen there. And now, by observing them on the largest photographic plate ever, that is our full sky, which is accessible to us, we see these moments which are, well, not the billions, but the billions of billions of billions of billions of a second after the Big Bang. We see and photograph it, and we see what happened there. That's just majestic. And now you may also interpret them. You see how many large spots, how many small spots, and what inflation predicts, because these are inflationary perturbations which predict the spots. And these blue points are the points which tell you experimental data about the distribution of these spots on the sky, how many large, how many small. And this red line is a prediction of one of the simplest models of inflation. So then you see it, oh my God. Okay, so then you summarize many different predictions which inflation made, and you compare it with observational data. One of these predictions that the universe must be nearly flat. That is because the radius of the universe becomes exponentially large. And this flatness is characterized by some parameter omega. 20 years ago, people were saying that omega is equal to 0.3 and inflationary theory is dead. Now, the results of these experiments tell that it is 1, I mean, just literally 1.000, and this is accuracy with which it is measured. And several other, well, experimental results confirming prediction for inflationary theory. I will not go into detail, just trust me. That's so far so good and so very good. Okay? But then the question is, can we do it even better? And first of all, this satellite, even though it is no longer produce new data, it produces so much of the data that people are going to study them for another year and then make another data release of Planck. Each data release is spectacular. The first one was something about 35 papers. The other one was about maybe 25. How many? About that, right? Okay. So next one should be also colossal. So we are going to see what happens. We also are interested in something else, and maybe some of you have heard about it. This is B modes, which were almost discovered, maybe not discovered, nobody knows, but there is a good chance that eventually they will be discovered, though it's not quite certain, because in some inflationary models, the amplitude of these B modes is so small that they will not be discovered. We really don't know. Okay? But if they are discovered, this would be yet another confirmation after many other confirmations. It will be yet another and very important confirmation of inflation. If it does not come, it does not come. Because, yeah, as I said, there are many models of inflation which do not predict it. And here is how this data of Planck and other experiments summarized by this graph. So this area is the preferable area from the point of view of many experimental data right now. Okay? So you take a sum of all of the best experiments right now, and you look at this blue area, that's where you want to be. These points correspond to this nice quadratic potential which I invented in '83. So sad, okay? So this is blue, and this is me. Okay. This, by the way, a point which was predicted by another Russian physicist at the time when inflationary theory didn't even exist. It is called Stravinsky model. And here he is, at the center of that. And I got envious. So how is that? My friend Alesha Stravinsky, he is from the beginning, is here saying, can we just improve the theory a little, okay? And we invented a theory which is called alpha attractors, which actually cover every single point here. So whatever it will be, Stravinsky will be sitting here. But I can be here if it is experimentally true, or I can be here. What is the meaning of these theories, which are called alpha attractors? It is not going to be extremely painful. It's going to be okay. So this is my standard, normal, simplest quadratic, like pendulum. And this is what we do right now. We take potentials which here look like pendulum, but here approach a plateau. And that is enough. And that's actually good, because here you can stay a long, long time, and you are not falling, because everything is flat here, and the universe is still inflating, and then you fall as you should, so that should be okay. But do we have any justification for inventing these clusters of models except for experiment forces us to do so? And here we turn to art, okay? So, right, okay, why I'm talking here? This is one of the reasons. You know the name, right? Okay. Maybe you have seen the picture. And this is the picture which shows here are some angels and devils. And here they are all large. And then you go in this direction and they become smaller and then big. And you can continue eternally. This is so-called planetary disk. So Escher asked mathematicians, can you suggest me something really challenging, really beautiful that I would work on? And they explained him a couple of things, and he himself was a good mathematician. So he made these pictures, which later have been reproduced by computer graphics. And this is actually a computer-generated image, okay? So, and they found that he was amazingly accurate in representing it. So what it is, it's something which is called hyperbolic geometry. So you have infinitely many devils and angels here, but most of them are concentrated on this one. Normal geometry would be just infinite disk, infinite radius. But with hyperbolic, that's what you see. And this is my potential, okay, my quadratic potential. And I just, using computer, projected image, whatever, and this is how it looks. Most of the angels and demons, they like to live at the upper part of it, okay? And then what does it mean? If we, the meaning is that the distance from this angel to this demon is the same here as it is here. It's just geometry of space is different. We need to find some way of expressing it in different terms. And so what you do, you just do something like that. You stretch the upper part. And then these demons and angels find lots of space here, and you stretch it infinitely. So instead of this nice bowl of soup, you have this picture, okay? And this looks like that. So yeah, if this is the scalar field, it stays here for a long time, it falls down here. Here it's almost like quadratic potential, but the fact that you are here are these fluctuations which are produced. They are generated mostly on the upper part, and the results, if you are in this theory, feed the data. What if we start with more complicated potential? Instead of saying having something nice, smooth, round, you just make it chaotic, whatever. But understand that this is a boundary. Just like this Planck disk, this is a boundary, you cannot go any further, and you must stretch it. And if you stretch it, this is what you get. In the center of it, nothing changes. But the boundary moves exponentially far away, and here flat potentials. And if you roll along these flat potentials, you get results of inflationary theories which perfectly fit experimental data. So is it physics, is it art, is it mathematics? I don't know. But all of these inspired each other. All of these appear to be helpful. And as a result, that what we have and this is now the set of the predictions of this set of models. So we're really happy about that. But I did not even start talking about the multiverse, right? Okay, so what we now have, if we believe into this set of theories, we have a theory, inflationary cosmology, which explains uniformity of the universe. So uniformity is done, okay? But then the same theory, interestingly, predicts that if we assume inflation that on a much larger scale, the universe must be 100% non-uniform. And the reason is that if you go very far, then this field does not know, shall it fall down, shall it not fall down, quantum fluctuations occur all the time. It may push even further along this valley, along this infinite, well, stretch of space of, it's not space, it's space of fields. Anyway, so it moves in this direction, could. If that, it falls down much later. What does it mean? That the universe, due to quantum fluctuations, this scale of field may move back to the higher regions of energy, and then inflation restarts there. And then it restarts again. It becomes eternal. Our universe becomes a multiverse. It self-reproduces itself. Instead of being a sphere where everything is so nice, it becomes a sphere producing new spheres, producing new spheres. So inflationary universe becomes a multiverse. And here is the simple example of multiverse without requiring any quantum fluctuation. I used to explain it to my European colleagues because what you do when you come summer to Europe, they just have a war all the time. Not real physical, but, well, physical, all right. They all play football. And then they have this football, and they have multicolored, not so many colored, but nevertheless. So look at this part, think about it like a universe, okay? And then this universe becomes exponential large. Within 10 to the minus 35 seconds, it becomes this one, okay? Now, I'm living here, I'm looking around, and I see white universe everywhere around me. And I'm concluding, because this is the only thing that I see, I'm concluding that the universe must be white. And let me try to construct a theory which explains that God did not have any choice but to construct white universe, okay? Somebody else living here look around and say, blue universe, everywhere blue. Let me try to explain why the universe must be blue because there is no choice. Somebody else, well, historically I was actually living somewhere here. And, okay, so what do you say when the person tells you that the universe must be red because there is no other choice? And even if it was in the beginning, that it's temporary choice. Okay, so we prefer multiverse. It is possible to live in peace, in blue, in yellow, in red, and black, until proven wrong. This is a more generic situation. Just look at yourself right now. All of us are described by strong interaction and electromagnetic interaction, just two laws of physics. Look at so many different colors, okay? Who can forbid you buying clothes of different colors? It's okay, despite the fact that it's the same law of physics. Look at water. Water can be liquid, can be solid, can be gas, okay? So now, if you're a captain of Titanic, and you are using your ship at night and you believe that water must be liquid, guess what happens to you? Okay? Because sometimes you meet different types of water. So here is what pessimists will tell about that. He will say that if each part of the multiverse, that's what we have, is the universe consisting of exponentially large countries, just like China before internet, okay? Person there would not know anything about Australia, okay? Now we know. So pessimists will say that if each part of the multiverse is so huge that we will never see its other parts, it's impossible to prove that we live in a multiverse. And that is why the multiverse is dangerous for community. Okay. Optimists will say, if each part of the multiverse is huge, we will never see other parts, so it's impossible to disprove that we live in a multiverse. I think that this last part is much more important because Einstein said something about it. I would rather be an optimist and a fool than a pessimist and right. So I say let's try to be an optimist, okay? Because this is the basic. Until we have proven that all colors are impossible, instead only gray is possible. Then you say, I will buy red and blue and whatever. I know that some of my compatriots coming to US, they go to Safeway, and I heard the story, I have not seen it, that somebody collapsed near the shelf filled with different types of coffee. Because the decisions to choose between hundreds of different types of coffee sounds terrible. You cannot just, you don't know what is in it, okay? Actually, Pascal, I have heard, said that during a lifetime, the person is capable of making only a limited number of decisions. After he's done, okay? So, but this scenario is much more general. Until you forbid something, then it is allowed. And that is, again, something which I learned when I was in Russia. One of my friends told me, you know what is the difference between Russia and the United States? In Russia, everything which is not explicitly allowed is forbidden. In the United States, everything which is not explicitly forbidden is allowed. So until somebody explicitly forbids the multiverse, it is allowed. But moreover, if you take into account quantum fluctuations, even if you start with the red universe, quantum fluctuations always create areas of blue inside it. And then inside of blue, you have areas of white. And inside of areas of white, you have areas of red. And each of them is exponentially large. And therefore, all possibilities are sometimes realized. And this is some, theory which I've studied back in '83. This is called supersymmetric SU5 model, never mind the names. It allows you to live in a place where there is no difference between weak, strong electromagnetic interactions. It allows you to live in a place with different types of laws of physics. Actually, there is one theory, but it's just realized differently. Laws of interaction of particles here and here are different. Here there is no difference between protons and electrons, no fundamental difference between quarks and neutrinos. And here we can live. This is our part of the universe. And then just imagine that you have inflation, and during inflation you have quantum fluctuations, and this field jumps to this region, to this region, to this region, back, and the universe becomes divided into many different exponentially large regions. I actually, when we made these computer simulations, I called it condensed universe in the name of the famous Russian abstract painter. So this part is exponentially large, and if you can live here, you live here. This part is exponentially large, this part is exponentially large. They all have been produced from one red-colored universe. Alan Guth, in the beginning, he invented the first version of inflationary theory, famously said, it is said that there is no such thing as a free lunch, but the universe is the ultimate free lunch. He said that, and he is multiply cited for that. And at that time, I was at the conference in Cambridge, which was the first conference on inflationary theory, and I was duly impressed by quality of free lunches served there every day. And I said there that the universe is not just a free lunch and eternal feast, but all possible types of dishes are served. Because if you have the possibility of red and blue, then you have all of them. You start with less than 1 milligram of metal, practically with nothing. And then you get all of these dishes. You can live in whatever place. And then it allows you to explain the meaning of entropic principle. It's just like on the Earth, dolphins can live in water. We can live on a dry land. And there's nothing wrong with dolphins, okay? So when we see that we live on a dry land, we should not insist that everywhere the earth must be dry. Thanks God there are some lakes around, whatever. So this is good. And we live in the part of the earth where we can live, and dolphins live in a place where they can live, which is also good. For us to create the conditions for different types, whoever live, you need the universe which have different properties. And we divide, the universe itself divides itself into exponentially large countries, which are so large that from the interior of each of the countries, you do not see anything else. So you think that this is your universe. This is just a part of the huge multiverse. For almost 2 decades, this idea, nobody liked it. People actually deeply hated anthropic considerations. This was somewhere deeply in blood. I believe that this is not Russian or American or something. It's probably something monotheistic. God must be one God, and if you do not believe into this God, then I will fire you and all of your relatives, etc. Right? Because the truth must be one truth, no many truths. Well, so then if you are talking with people from Indian origin or Japan, they will say, what? They may not understand this insistence on that the truth must be for everyone must be the same. They will tell you something else. So anthropic principle was extremely unpopular. People in physics were proudly saying, I am not using a word in my paper. They would not even say anthropic. This was so despisable. Okay? They would say a word like this, Voldemort, right? You don't say it. Okay? So what happened, however, in 2003, we found that in string theory, which is supposed to be a very, very prominent theory of everything, you just have this. You have many different possibilities. Like in water, you have 3 possibilities: solid, liquid, gas. Then in string theory, we have 10 to the degree 500 or something possibilities. And then when we learned it, and why this 10 to the 500, where they come from? Because our universe, according to string theory, is 10-dimensional. Now, 10-dimensional, we live in 3-dimensional world and 1 dimension of time. Where are the 6? Other 6 are squeezed into something very complicated. Usually people are talking about some special spaces called Calabi-Yau space. Does it work right now?
No.
Okay. Okay. So I heard about the construction a long time ago when I visited Andrei Sakharov, who was a famous Russian dissident in Gorky. He was in exile, and we were sitting at the sofa there, and he was discussing with me all this compactification. At some moment he said, but look, if there are many different ways of compactifying this extra dimension, it must be combinatorically huge number. And he wrote a paper saying that if you have that many choices, then you have so many different possible values of energy of nothing, vacuum energy. And then we know why vacuum energy is so small. Because if energy of vacuum is large, then it would be instantly dead. It will be torn apart by rapid expansion, inflation of the universe. If energy density of the world is large and negative, we would instantly collapse. So we live in one of these many layers which are allowed by different options for compactification. And then string theory realized this idea by producing this kind of strange configurations. And the idea was that you have in string theory many different minima of the potential energy, depending on what happens at some fundamental level with this compactification. And we live just in this narrow corridor which allows us to live. So anthropic principle is heavily used right now by modern physics. Can we test the multiverse theory? Well, this theory right now, I would say, is already experimentally tested, have been experimentally tested. We are testing it all the time. Example, this theory is the only theory which explains experimental data. Vacuum energy is so small. By the way, why electron mass is so small? Electron mass is 2,000 times smaller than mass of the proton, mass of the electron, mass of the neutron. Okay? If it were 10 times larger, 10 times smaller, we would be dead. So mass of the electron is unnaturally small, but it is just right for our existence. Why the difference between proton mass and neutron mass is less than 1% of their mass? If proton would be 1% heavier, then all protons would decay and you would have only neutron stars, no people. If neutron would be 1% heavier, all neutrons would decay and there would be no heavy nuclei, only hydrogen, no people. So there is adjustment between this unnatural tuning of these parameters and our life, and many stories like that. You need to have ground for this anthropic explanation, and so far the only way to explain it would be a combination of inflationary theory and this multiverse construction. So, because this is the theory which provides the only known explanation of experimental data, then this theory has been already experimentally tested. But then some people say, but this is not serious. Real science must be falsifiable. You must make a prediction which is explained only by anthropic principle, which isn't explained any other way, and then after that we may believe it. But this famous philosopher had a different attitude to that. He said that when you have eliminated the impossible, whatever remains, however improbable, must be the truth. And that's how American system of justice works. If somebody kills his wife, you do not repeat the experiment. You do not give him another wife, another knife, and check what happens. No, instead of that, you collect all available information, and then you make the decision. And if you are convinced beyond any reasonable doubt there is no alternative explanation, then you send the person to electric chair. Well, so what does it mean? This means that our judicial system is not quite scientific, but it works. So we should not say science should work differently. We have this evidence, we have this experimental data, which do not have so far any experimental evidence. So when we say multiverse, and we do not see this other part of the universe because it's so far away, and therefore we will never have any evidence in favor of it, I would say, let's be optimists, we already have this evidence. So this would be the time when I will finish, and I will not talk about anything else right now, except for maybe, if you give me 3 more minutes, I will tell you a funny story, which I myself did not expect. I was watching TV, and this was Bloomberg TV in the evening. Sometimes I'm just watching about this gray-haired person. Should be nothing special for me, of course. What is his name? Very smart commentator, Charlie Ross. Okay, and he was talking with some famous woman physicists. She was looking beautiful. She was talking smart about parallel universes, etc. And then in the end of his talk, he said, everything was just finished. He said, but Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. And she shut down. She could not know what to answer. And he emerged like a winner. All of his science is bullshit, because even Einstein did not know the first thing about it, that it is not even know why you should believe to any of that, all of these laws of physics. Then I decided to check, interesting, and I looked. This is Eugen Wigner. He is a famous mathematician. He said, the unreasonable efficiency of mathematics and science is a gift we neither understand nor deserve. So this is humiliation in the face of God, who gave you the universe which is describable by mathematics. And I thought something is wrong with it. Let me see what the modern mathematicians think. And that is some person who immigrated, was living near New York from Russia, famous mathematician Gelfand. He said there is only one thing which is more unreasonable than unreasonable effectiveness of mathematics and physics, unreasonable ineffectiveness of mathematics and biology. So all of them are saying there are some miracles around. They don't understand what is going on. Okay? So the reason why they consider it all miracles is that if the universe is everywhere the same, and that was ingrained in philosophy of all of us for years and ages, in fact, okay, they put the Giordano Bruno on fire because he had some lingering doubts about that. Okay, so maybe for some other reason. So if the universe is everywhere the same, so if we do not have any choice, then the fact that it obeys so many different laws is really, really very strange. Okay? And these laws are working so good that we're going to say, oh my God, it's undeserved gift of God who created not only the universe, not only us, but us and the laws working so nicely that we mathematicians can earn our money and not work in the field. Okay? So now, if you have inflationary multiverse, this problem kind of, at least, almost totally disappears. What does it mean? Well, in inflationary multiverse, there are parts of the multiverse where energy density is huge, so huge that quantum fluctuations, even now as we speak, are so large there that they totally destroy all information produced there. So there is no recording devices are possible, there are no memory possible, there is no mathematics is possible there. There are no laws of physics which are preserved because everything is instantly erased. There are some other parts of the multiverse where there's total vacuum, no human beings, nobody flying there, remembering anything. So there are some parts of the universe where computers are impossible. But we live in a part of the universe where computations are possible because they are necessary for us personally, for us to win the game of evolution. That is why we can live only in a part of the universe where stable information processing is possible, and memory is possible, and using this memory for predicting the future is possible, and that is physics and that is mathematics. And that is why there is nothing surprising in what we see. It's not a gift of God. It is just a condition which we, well, anthropically impose on the part of the universe where we can live. And somebody else can live somewhere else, but they will probably not be physicists or mathematicians. So this is my last transparency. This is the structure of the universe as we think about it right now. Previously we thought that this is one balloon. Now we think that this is a balloon producing new balloons, different colors all together, huge, exponentially large, ever growing, never going to disappear. It is eternally growing fractal. Okay, and then in some parts of this multiverse, physicists can live, and in other parts they cannot live. They look around and they say, why laws of mathematics are so mysteriously good? And I hope that we know now, or at least we have a glimpse. Okay, thank you so much.
We have time for a few questions. If you want to ask a question, please come to one of the mics in the aisle.
You mentioned some non-physicists who have criticized inflationary theory, but some serious physicists such as Paul Steinhardt, who contributed to the theory in the early days and were major proponents, have become severe critics. Can you explain what this criticism is and why you presumably don't share it?
Well, I think that here we deal probably not with physics but with sociology, which is very difficult to explain. But really the situation is as follows. Paul Steinhardt indeed contributed in the early stages of development of inflationary theory, which means the following. I invented something which is called new inflation. I sent a copy of my paper to the United States, and 3 months later it was independently discovered by Paul Steinhardt with Albrecht with a reference to my paper. Okay. After that, he also continued doing some interesting stuff. He is a serious scientist and not only in inflationary theory. But after a while, he started trying to invent an alternative to inflation. And starting approximately with the year 2000, he have written lots of papers on alternative scenario, which is called a periodic scenario. We received his paper when it was produced as a thick paper about how you can solve all cosmological problems without using inflation. We looked at it, it looked absolutely spectacular, just gorgeous. We start reading it. When I say we, this means me and my wife, Renata Pavlich, who is an expert in string theory and supergravity. and I'm in cosmology, and she is reading it and saying, but I don't understand where this came from. And I'm reading and say, I don't understand where did he take this is just wrong. And then after reading and reading and reading, these papers start disintegrating in our hands. Okay, so we've sent a paper explaining why there are so many different really bad mistakes there. Eventually, they made a mistake such that they thought that the universe is expanding, but it was a collapse. So just change a sign in the evolution of the universe, totally strange. Okay? And then they start changing the story, because when we explain them that your universe is collapsing instead of expanding, they say, okay, that's good. Now we solve the singularity problem. And they said, we already solved them. And different people checked, and they found, no, they didn't solve it, and this was wrong. And then I've written another paper, and another paper was also wrong. And I continue, like, once a year, producing new and new papers, and I checked many of them, and every single paper which I checked was just incorrect. Okay? So then, well, whatever, you just give your own explanation of why the person who was trying for so many years invent theories and they do not work, and more or less they are well taken aside by scientific community. People who do these Planck satellite stories, they admit somebody talking about alternative theories in their conferences, but mostly when you read what these Planck satellite have written, their papers, there will be like one paragraph mentioning why this particular version of alternative models does not work. Okay? But that is it. Therefore, if you ask them, why do you do that? I don't know what exactly they would respond.
So, my question is it possible that in certain regions of the multiverse, the physicists there can actually get a better view of the multiverse and maybe even interact with other regions of the multiverse, including, well, basically, can they have better telescopes and better instrumentation to view other regions of the multiverse? Is that barred, or?
Well, unless you know how to build a wormhole, and through this wormhole travel to our part of the universe, it's very hard to imagine that they can come to us, because the way travel goes, when you travel and the universe continues expanding, and you travel and continue expanding, it's very difficult to come to the final destination. So it's very unlikely that we are going to witness other parts of the multiverse, but not totally impossible. It is possible that these parts are not 10 to the degree 1,000, whatever, million times large. They may be just exactly right large, so that we can see them not in, well, in our garden, but in, well, at this edge of the presently observable part of the universe. Maybe you will see there are some experimental proposals how you can actually see these other parts of the universe on the horizon.
So that means the property of actually having the difficulty of building a wormhole is uniform throughout the multiverse in the underlying principle that has to stay the same.
It's just difficult to travel with a speed faster than the speed of light. Each time I tried, never worked.
May I ask, so you were discussing how the explanation of the miracles of the miracles was that you need the universe, for us to occur in the universe, we have to have predictability, and so we will naturally have predictability occurring. We'll have mathematics and logic and causality, and then in perhaps most parts of the multiverse, there is no predictability. And does that mean? I mean, that would imply that there's no causality. Is it even possible to have mathematics in these vast regions and logic? These things break down as well, because those seem to depend on the same things. And so my question is, how is it possible to have a self-consistent meta-theory of the multiverse when it seems the very tools you use to create this meta-theory break down outside of your local regime?
So first of all, the story which I was talking about, this multiverse consisting of different countries with the laws derived from the same fundamental law of physics. In this fundamental law of physics, you do have causality, you do have all necessary laws of physics required, you have quantum mechanics, you have all gravitons, unavoidable perturbations of space-time. They all travel with the speed equal to the speed of light, and they cannot travel faster than that. So these principles are valid in all of these places, but realizations of physics, nevertheless, may be quite bizarre there. The examples which I gave you is that despite the existence of these basic structures, you cannot use these basic structures for memorization, for prediction, for even say the word laws of physics. You stop saying it because you're dead while you're talking about this. Okay, so this just tells you that even in this primitive setting, and I emphasize primitive, because I was based it on the assumption that there's one fundamental law of physics. In these normal kind of settings, you already have this 10 to the degree 500 different options. But you may ask a more fundamental question, and this fundamental question is for us to consider seriously and maybe come with some more complicated answer. Like, for example, suppose that the universe started its existence at some moment, okay? So when we're talking about laws of physics, I understand, okay, so there is something which I can write on the blackboard, and this is some equations which I can solve, explain to others. This will be a law, okay? But if the universe was not even in existence, then where the universe laws can be written, okay? And if they could not be written, is it conceivable that the universe was expanding totally lawless? So what was first, the law or the universe? And is there any sense discussing universe without any observers looking at it and talking about the laws? There is some good reason, really, to think that the universe unobserved, there is no meaning in which the reality of such a state can be asserted. We see evolution of the universe only because you divide the universe into two parts, and the wave function of the rest of the universe is depending on the clock on your hand, which I don't have right now. Okay, so reality, the way how laws of physics appearing, maybe they appear like triples, and that is the universe, the laws of physics, and you observing them, and you cannot just, ignore these possibilities, and maybe all possible, logically possible options are in existence. So if you open the book by Max Tegmark, he will tell you something about multiverse, which are just different laws of mathematics. Whatever. So many different possibilities. I was taking, if you did not notice it, that I'm saying it, I was taking very conservative point of view.
I have two questions actually. My first question is, what is dark energy or dark matter? And the second question, which one is older, universe or stars?
Okay, let's start with the last one. Stars are a part of the universe, and therefore the universe is older. Okay. As for dark matter and dark energy, the short answer, we do not know. The long answer is that for the dark energy, most probably this is just the energy of vacuum state. So it's just an empty state, empty box filled with heavy nothing. Okay, so there is no real particles going there. It's just this energy of, or maybe energy with scalar field, whatever, something like vacuum. Okay. Now, as for dark matter, it's matter, but it is dark. Okay, so it's no kidding, because every kind of matter which does not interact with photons, it's okay. Neutrinos do not interact with photons. So if we have anything like, say, heavy neutrinos, or not even heavy, light neutrinos, They could be. They are actually right now totally disfavored as the possibility for dark matter. But it just give you an example of what is matter, which is dark. Now the most advanced version is something related to supersymmetric particles, some super heavy particles with the mass maybe 100, 200, 300 times heavier than a proton. Maybe another possibility, there are some other field which is called axion field oscillating. So there are many different possibilities. We don't have, unfortunately, any idea what it will be eventually, but some of us are persistently searching. Peter Michelson, who studies what happens in different parts of the universe, what kind of signals or decays of real particles may appear here. Maybe eventually we will know. If you want to know details about it, read New York Times, it will tell you everything about that. Today there was an article about dark matter, which tells you that it is very dangerous because it produces cancer, and therefore if you study people who are ill with cancer, you will learn something about dark matter. Whereas you say, interesting.
We'll do two last questions. Try to keep them short, please.
Those different parts of multiverse, they have different laws of physics, or for example, the mass of particles might be different.
Could be.
What happens on the border? Or
Okay.
is there a border actually?
Depends, okay? Because there are some, just like in real life in the Earth, so sometimes you go and you just cross from United States to Canada without noticing, but then if you go in the wrong place, then you first meet a policeman. Now, in between these different countries, most of the time, you have a domain wall. Such a domain wall that when you go from one region to another, laws of physics are changing, and it is often happen discontinuously. It's not again like laws of physics are changing. It's like laws of chemistry are not changing when you go from liquid water to solid water. But something very dramatic happens. And usually it's very difficult to penetrate from one area to another. But if you're young, bold, and energetic, you go through this, and then most probably you die there because your particles will not exist in other parts of the universe. But there are some other options where, say, the amount of axion field slowly changes in different parts of the universe, and you can travel from one to another, and then what happens is simply the fraction of mass of the universe in dark matter changes. Here it is small, here it is large. You can live in one place, you can live in another place. If you have too much of dark matter, you will have totally different creation of galaxies, but you possibly can live there as well. So at least you will not die instantly when you travel.
Andrei, what happens with time actually in the multiverse?
Time ends. Okay. No. the nice story about this and the sad story about that. Before inflation, we had two different choices for the cosmic death of everything. First, if the universe is closed, it collapses and we all die in fire. Second possibility, if the universe is open, it expands and we all die in cold. Okay? Then with the discovery of dark energy, people concluded, maybe too fast, say that even if the universe is closed, it is going to continue expanding forever, so it's guaranteed die in cold. But when we studied this theory of string theory, what happens is that always our vacuum state in all versions of the theory is metastable. Metastable means not totally stable. There will be bubbles of new phase appearing, and inside these bubbles you will see different parts of the multiverse with different properties. They will come to you and they will kill you by this bubble, okay, and they will not report to anybody what happens. Okay, so they continue propagating. This is the way to die. But then inside this bubble, different properties of physics, so you would die if you live there, if it is negative energy, and eventually everything goes to the state of with negative energy not returning back. In a negative energy, this part will collapse and will die in fire. But there is another interesting possibility, and another interesting possibility to to 10-dimensional space. And in string theory, this is one of the preferable possibilities. And in 10-dimensional space, you will not be able to live because in any space with dimension different from 3, back entropic principle, in any dimensional space different from 3, planetary systems and atomic systems are unstable. Okay? This fact was discovered in 1917 by Paul Ehrenfest. But to put it into the context of some physics where it can be used, we need to have this development of inflationary string theory to make it sensible.
All right, so in our part of the universe, we're out of time, so please join me in thanking Andrei Linde.